Alright, here we go. OSU Tulsa, 2011. 11, yeah.
But we'll tell you what we think it is, and then we'll go weigh it in the middle's lab.
Okay, go ahead and do the introductions.
I'm Asia Moore.
Josh Cunningham.
Lance Moore.
Austin Roberts.
Daniel Childress.
This is our mass flow detector. We've got basically just a venturi. We've got a 1.5 inch pipe that goes to a 1/2 inch pipe. We have a silicone dioxide pressure sensor that measures the differential pressure between the two. Since we know the area, the cross-sectional area of the small pipe, and we know the differential pressure and the density of the fluid, we can calculate a velocity. Also, then when you take the density in the area, it gives you a mass flow rate. This pressure sensor senses all the way down to 1 kilopascal, and it'll give you an output between 0.2 volts and 4.7 volts. It's got a 0.2 volt offset. So the very first thing we do is we strip that out with a 0.2 volt subtraction on a difference op amp. We then use one proportional op amp to take into account all the conversions of density, metric units to customer units, so that what our output is, the voltage is directly proportional to pounds mass per second. We did have one problem. We couldn't get a square rooter to work. It's a complicated op amp, takes 3 op amps. We couldn't troubleshoot it, so our output is actually the square of mass flow rate. So if the output's 4 volts, you're getting 2 pounds mass per second. The most useful measurement, what we're lined up for now, is we're taking that output into an integrator with a gain of 1. It will integrate that mass flow rate over time. You don't have to do this, but we're going to time the amount of time it takes us to fill that jug halfway full, and we're going to read off the integrator's output. So we will have to do a calculation since we can't do a square root, and that'll tell us how many pounds mass we think went through. And then we'll go weigh it in the metals lab and see if we were right. Okay? So it takes a little coordinated effort if you have to time it. What we're going to do is, when I open the valve, don't pour anything in. When I open the valve, we're going to start the timer, and Lance will mark the final value on the integrator. Right now the integrator's shorted, so it is at 0. It's not accumulating any air. He'll mark the final value, and with the time and the final value, we'll be able to tell the pounds mass that passed through during that amount of time. Are you ready?
I'm ready. You ready, Austin?
I'm ready.
All right, 1, 2, 3, go. One, two, three, stop.
3.05 volts.
All right.
8.9. So it requires a wire being pulled over there to start the timing circuit?
Yeah, I keep the integrator shorted. If you have small differences, even a few millivolts, it starts adding the air to the integrator.
Now there's not a timing circuit in there though.
No.
Okay, so you didn't need a 555.
No, it was just a...
Can you talk a little bit about the actual physical sensors that are in here, and were there any trouble spots, anything that you had to work through, or did everything go exactly to plan?
This was a result of everything not going exactly to plan.
Right, well, originally, as I recall, you were doing this with gas, and the fact that it was compressible.
It just led to
you not being able to determine the density.
To stay pressure tied and to get measurements.
Okay.
Water, since it was so dense, made it so the flow rate didn't have to be as fast. The faster the flow rate, the better this measures, because we're still down on the low end.
Okay.
500 kPa is what this goes to. It's about 70 psi. We only get to the output closer to like 9 to 10 kPa. So we're on the real low side of this. In hindsight, we'd get a much more sensitive.
And we don't have to be, you wouldn't have to go down to the materials lab and weigh this, but you've done tests for this, I'm sure, for a number of samples.
Right.
And so you get a reading over here that tells you what the mass flow rate, or what the total mass that's gone through here was.
Yeah, that
and
was...
then you verify this based on the amount of time, the amount of water that you get by weighing it.
Right. And what we could have done if we sampled off the end of the proportional is got an actual real-time mass flow rate where the voltage you saw was the square of the pounds mass per second.
Okay.
So you could get both a real-time...
How accurate was this?
We were always about 18% low.
Low.
Low. Yeah.
What do you think was the result of that?
Well, we made one assumption to make the calculations easier, which is in the Bernoulli equation, we assumed that the velocity on the high pressure side was 0.
Mm-hmm.
It's not true, but the area is about 9 times as large, so this velocity is about 10% of that velocity. That's going to lead to some error, and the faster you flow, the more accurate, and since even though it looked like we were flowing pretty quick, on the slow side, the higher the error got.
Can you talk a little bit about your pressure transducer here?
Yeah, this was just...
Where'd you purchase it? How much did it cost?
This is about somewhere between $10 and $12. It's a company called Freescale. There's a silicone wafer inside. You don't have to use it. It's just basically through the change in resistance as you apply pressure to the piece of silicone, you will get an output voltage, once you strip out the 0.2 volts, proportional to 9 millivolts per kPa. Okay. So you can hook up a low pressure side to it, and it'll just go to straight differential pressure instead of absolute. That's all we needed for velocity.
And then my last question is, there was a little bit of a coordinated effort here to get the timing over here. You did the stopwatch. You pulled a wire over here. What sort of steps would be required to automate this a little bit more to where it's something that you could put into a working system and with the press of a button, from someone who was using it, have it more, usable by one person with just a button?
Ideally, what we were looking at the mathematic analysis of seeing the accuracy. We wouldn't really, you would use that once to see if it's an accurate measurement, but really we would tap off the proportional to just have a voltage. If the voltage was connected to a meter with a dial, you're going to look and see the current mass flow rate in a system that was constantly moving fluid.
So the timing portion of it
was just to check out
was purely for the ability for us to say that is 5.8 pounds mass, and we go weigh it, and it was pretty close.
Okay. And so ultimately you would only display, as you said, the proportional value. That way if the valve's open and there's fluid flowing through, you've got a reading, and that's equal to the mass flow rate that's going through there.
So equal to the square of it.
Okay. And then if you were able to build the complicated circuit,
square root of it.
The square rooter, which you said involved 3 PIDs or 3 op amps?
No, 3 op amps. So basically a logarithm, divide it in half, and then take the analog, and you've got the square root. But it uses some transistors and a lot of capacitors and not a lot of data points to troubleshoot to see what portion is incorrect.
Okay. Questions from anyone else? No questions. Okay, great. Well, thanks.
We're gonna see if we got one.